So welcome to Math 331 problem solving. This is lecture 26. And so what I want to do today is talk a little bit more about Putnam A1 problems. So one of the nice things about saving the slides is it's very easy to toggle backwards and just look at what we were doing last time. So last time we were looking at A1 from 2017. Let us be the smallest set of positive integers such that the following three conditions hold. What positive integers are not an S? And so we started talking a little bit about how can you come up with a good tree structure? How can you come up with a good way to look at things? And so when you look at what's going with 2, you have 2, 49, 49 splits to 754. 7 has to go to 144, but then from that you get 12 and 149 squared. One way of looking at this is if I start with 2, I know I'm going to get 7. And if I have 7, I know I'm going to get 12. If I have 12, I know I'm going to get 17. So I'm going to get all the numbers that are 2 mod 5. It has other numbers in there as well. But so one way to look at this is to say, I know I have all the numbers 2 mod 5. And once you have some number, you have every number that is congruent to that mod 5 from that point onward. You don't know if you have the earlier numbers. But because we can keep adding 5, we know once we have a number, if it's 3 mod 5, then every number that's 3 mod 5 from that point onward has to be on the list. So another way of looking at this is to say, if we can show that there's at least one representative of 1, 2, 3, 4 mod 5, and if so, what's the smallest representative, then we'll completely get it, because we know we can't have anything that's 0 mod 5 in the set. Why? Well, we know, we start with 2. If n is an S, then n squared is. So if you're not a multiple of 5, squaring, I'm sorry, so you're in S if n squared is in it. So if n squared is not a multiple of 5, n is not a multiple of 5. And then n plus 5 squared is an S whenever n is S. Well, if n is not a multiple of 5, then n plus 5 is not a multiple of 5. So we know the set is not going to contain multiples of 5. So the question is, which multiples can go into 1, 2, 3, and 4 mod 5 does it contain? We just showed it contains all multiples of 2 mod 5. 49 is the same as 4 mod 5. So we know it has all multiples of 4 mod 5 from that point onward. So then the question just becomes, is there a smaller number that's 4 mod 5 that's in the list? And just thinking about, when we square things, how does that change what you're congruent to? So it turns out, if you do the analysis, I believe you can show, I think every number that is not 0 mod 5 is included. I think so, because again, the key thing is that if n plus 5 squared is an S, I'm sorry, n is an S whenever n squared is an S. So we've got n plus 5, we square that. And so the question is, can that ever be like a 4th power? We know it's not going to be a 4th power when we look at n is congruent to 2 mod 5, but maybe for some of the other stuff. And so I'll leave that for you guys to just think about. But I want you to say a few more words and just try to talk about how would you look at these problems. And for stuff like this, it's definitely a congruence problem. And the fact that we're adding 5 is basically telling us we want to look at things mod 5. And we notice that nothing that is 0 mod 5 has to be in the set. So I have posted 3 problems here. I've squished them to get them on the board. From 1994, we have a sequence such that an is positive and it's less than or equal to a2n plus a2n plus 1. We want to prove that the sum converges. From 89, how many primes among the positive integers written in base 10 can be written as alternating 1s and 0s, beginning and ending with a 1? Well, we don't really need to say beginning and ending with a 1, because if it ends with a 0, it's not prime. And if it starts with a 0, we could ignore that. So they're just being, I don't know, 23, for positive integer n, let fn be the product of cosine x, cosine 2x, cosine 3x, all the way up to cosine nx. Find the smallest n such that the second derivative is greater than 2023. This has all the structure of a classic problem. At some point, the year of the exam should occur in one of the problems. So you should immediately know going into an exam, is the year prime? If the year is not prime, what is the prime factorization? That may not matter. What's the nearest prime to your year? So 2024 is clearly not going to be prime. But you should know what's the next prime after 2024. The one from 2004, and my son has actually met the basketball player that this is inspired by, is actually a very famous problem that's been I think that's had a lot of discussion. It's a fun one. Basketball star Shaneil O'Keefe has a statistician on their team who keeps track of how successful she is making free throws. And she starts off the season less than 80%, finishes the season greater than 80%. Must she have been shooting 80% at some moment in time? And then the last one is the one we've already done. So these are problems that I particularly like. Of the ones that I've listed here, if I had to choose a favorite, it would probably be 2004, followed by 2023, followed by 1989, followed by 1994. Basically in reverse order from which they're written. If anybody has any preferences, your preferences override mine, but that's the order in which I like them. Anybody have any preferences? The primes? All right. So now we will see if this works. I'm hitting copy. I'm coming over here. Okay, it actually did work today. Okay. So what's the first thing you should do for a problem like this? What's the first thing we should do? And all of these problems, step one should always be the same. How should we start? Gathering data, right? Step one is gather data. So the numbers are going to be 1, 101, 10101, 1010101, 1010101, dot, dot, dot. All right. 1, prime or not prime? Not prime. We do not consider 1 prime because if 1 is prime, we lose unique factorization. What about 101? Prime or not prime? So remember, if a number is composite, so if composite, you can write n as x times y with x less than equal to y and x less than equal to the square root of n. So if you have a composite number, it can't be the case that both of its factors are less than its square root, because when you multiply them, so you only have to check up to the square root. So I only have to check primes up to the square root of 101, which is a little bit more than 10. So I only have to check 2, 3, 5, 7. And it's not going to be divisible by any of those. So this is prime. What about 10101, prime or composite? So there's a fast way to tell if this is.
This is
I'm sorry?
This is composite.
Why is it composite? Yes, so composite. So digit sum is a multiple of 3. So in fact, we know that every third of these numbers is clearly going to be composite. Okay, what about 1010101? That's a bit harder, right? And there's a lot more things that we now have to start to check. So we can start trying to play some games. We know there's at least one. We know at least 1/3 of the numbers fail. So one of the things that you might notice quickly is let D equal the digit sum and assume D is composite. What do you think we could conclude? So imagine, for example, let's say D equals 6. So we have 10101 oh, okay, 6 is a multiple of 3. I'll do 10. 1 1 1 1 1 1 1 1 1 1. Do you think this is prime or composite? Why probably prime?
The digit sum is composite.
Right, the digit sum is composite. So the digit sum here is 10. So do you think this number is going to be prime or composite? And if it's composite, do you have any... So we have 2 copies of something like this, right? Each of those have a digit sum of 5. We have 2 of them. Could you think of something that you could multiply by? And can you think of a factorization of this number? You know, 1010101, that block of 5, should probably come into the factorization. And what could we multiply this by?
We need to have it as like 2 numbers multiplied to make that.
Well, if I want to show that the number with 10 ones is composite, one way to do it is to give a factorization. So if I can give a factorization, then I know the number is composite.
Oh,
101 doesn't have enough zeros between the ones. If I have 1, if I have 1, 2, 3, 4, 5, 6, 7, 8.
1 0 0 0 0 0.
So I'm going to cheat, and I'm going to just put a couple of zeros there, right? You need to figure out exactly how much it is. But if you do it just right, the green block will hit the first one, and that'll be the left part of your number, and then it'll hit the right part, that'll be the right part. So this shows how to do it if this digit sum is composite and a multiple of 2. If it's a multiple of 5 or whatever, I think you can see how you would do this. That you could just separate things out well enough and have the blocks not see each other. This still leaves infinitely many cases. And this is, in fact, not how you would actually solve the problem. And I don't know how many points they would give you for a partial solution like this, but this does reduces to digit sum is prime. Except for 3. But 3 is it just says we have to check those cases. What's a necessary condition to win the Super Bowl? Yes. Yes, you need to make it, right? And so, in honor of Professor Blackwood here, she is a fan of the Buffalo Bills. They hold the record for making 4 consecutive Super Bowls and losing each time. So they know that, it's not a sufficient condition. It's necessary, but it's not sufficient. So what this is telling us is that if the digit sum is composite, it's clearly not going to be a prime. That's not the same as saying that if the digit sum is prime, then it's prime. It just says those are the only numbers you need to look. So one way to attack this problem is to try to say, well, can I somehow use the digit sum to help? And we know we have this rule of a number is a multiple of 3 if the digit sum is a multiple of 3. And this reduces us now to trying to understand what happens when the digit sum is prime. Well, 101, that has a prime digit sum, and it's prime. 10101 has a digit sum that's 3, which is composite. So it's going to be a little bit harder. You could try to do 1010101. Okay, so let's continue thinking about this problem. So we have in general 10101 dot 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 01, and I can write this as the sum k goes from 0 to n of 10 to the 2k. This is just a nice way to write the number. What can you tell me about that sum? So this is just a finite geometric series. So this is going to just be 10 to the 2n plus 1 minus 1 over 10 squared minus 1, if I've done everything correctly. Yes? Okay, well, what do we know? Have I made a mistake? This is how you would factor it, right? This is how you would execute the sum. Another way you could look at this is you could say, this is an old trick, x equals 10101 dot 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 01. What would be a good thing to multiply x by to get a lot of cancellation? This is similar to how you prove the geometric series formula. If I multiply x by 100, I'm going to get 1 0, 1 0 1 0 1 dot 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 0 1, and then two zeros at the end. So if I subtract, I would get 99x equals, all those zeros, and I would have that minus 1 at the end. So that's another way to see that it is 10 to the 2n plus 1 minus 1 over 99. So again, you might have seen something like this when you're looking at what is 0.9999, what's 0.9 repeating. You multiply by 10, subtract, and everything cancels. So, okay. Can you factor 10 to the 2n plus 1 minus 1? So we can view this as, let's view it as maybe u to the 2n plus 1 minus 1 over 99, where u is 10. Can you give me a root of u to the 2n plus 1 minus 1? So let's do some recalls. If I give you a squared minus b squared, how would you factor that? A minus b times a plus b, right? So if I gave you a cubed minus b cubed, do you remember what that is? So if I fix b, what's the value of a that would make this 0? A equals B. So I know this has to have an A minus B as a factor. And then you see it's A squared plus AB plus B. And when you multiply through, the A is going to give you everything with a plus, the B is going to give you everything with a minus. Everything will cancel except the extremes. A to the fourth, so if I give you something to an odd power, then what I should have is a number, let's call this X. We should get X is going to be U minus 1 times U to the 2n plus U to the 2n minus 2, or 2n minus 1. I think 2n minus 1 plus dot 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 plus U plus 1. So since U equals 10, this is going to be 9 times 10 to the 2n plus 10 to the 2n minus 1 plus dot 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 plus 10 plus 1. And this should be divided by 99. So we've almost shown that X is composite. We know the 9 can cancel a little bit and make that an 11. The 11 has to go into the numerator. So the question is that prime? Do we have a factorization? So let's see. So unfortunately, we then need to show that what we have upstairs, some, bless you. Something, oh, wait a minute. Oh, it's not 10 squared minus 1. What should the denominator be? Where's it 10 squared? No, it is. We're doing 10 squared to the k. I think I did an algebra mistake. This is why it's better always to use like the letter R. I'm really using R equals 10 squared. Or I guess you were using U. And so it should be U to the n plus 1, right? So this should be U to the n plus 1 minus 1 divided by U minus 1, right? So I've got the wrong factorization here. It should be U to the n plus 1 minus 1 over 9. I'm sorry? Was it still 99?
I think the top is wrong, because it's like, before it was 2n plus 1, which.
Yeah. Let's turn the page and let's write it again. When you make this many mistakes, let's just start all over on a new page. So we've got x is 1, 0, 1, 0, 1, 0, dot, 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 1, 0, 1. And we want to write that as 1 plus 10 squared plus 10 to the 4th plus 10 to the 2n. So let's let u equal 10 squared. So x is going to be the sum, k goes from 0 to n of u. And that's going to be, 1 minus u to the n plus 1 over 1 minus u. That's the finite geometric series formula, which is the same as u to the n plus 1 minus 1 over u minus 1. Okay. And so, if we look at that, I think the second mistake I was making is I was plugging in u equals 10, where it really should be u equals 100. Should be u equals 100. Okay. So now when we put that in here, we see that there's going to be a u minus 1 that's going to cancel. And so that would give us x is equal to u minus 1. And then over here, unfortunately, it's going to just bring back the original sum. It's just going to then give us 1 plus u squared plus dot 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 plus u to the 2n over u minus 1, back where we started. So this was, somewhat promising at first, but we've actually ended up in a circular loop. We've come back to where we started. We have a nice formula for what's happening. We want something a little bit better. And so we need a better factorization where the u minus 1 is not being killed, because that just reduces us to where we started. Now, if we looked at 100x minus x, that's going to be 10 to the 2n plus 2 minus 1, right? That's what we saw before. Yes? And so this is the same as 10 to the n plus 1 squared minus 1. Okay, so now we have 99x equals 10 to the n plus 1 squared minus 1. How can I factor the right-hand side? Well, I've got the difference of two squares, right? So how would you factor a squared minus b squared? Good. 10 to the n plus 1 minus 1 times 10 to the n plus 1 plus 1. So we know the 99 has to go in somehow to stuff on the right-hand side. It's possible that it goes into all of the first factor, all of the second factor. Some of it goes into one, some of it goes into the other. But eventually, what's going to happen when n is sufficiently large? Eventually, each factor is greater than 99. And if each factor is greater than 99, then does x have to be composite? So we can write x as 10 to the n plus 1 minus 1 over a times 10 to the n plus 1 over b, where a times b equals 99. I don't know which way things split, but I know I have something like that. And so if I know each of these factors is sufficiently large, if each factor is at least 2, we know it's composite. So, if each at least 2, then X is composite. So how could 10 to the n plus 1 minus 1 over a be small? So, question. What makes 10 to the n plus 1 minus 1 over a small? 10 to the n plus 1 over b small. So what would make the first factor small?
Like the number, like that term.
Yeah, what would make that term small?
That is zero.
Okay, so if n is small, or what else? A is large. So the worst case for us is if a is 99. What value of n will guarantee that it's at least 2? So worst case is a equals 99. If n is 3, then you would have 10 to the 4th minus 1. All right, well, 10 to the 4th minus 1 is clearly going to be much larger than 99. So if you take n equals 3, you're fine. What if you take n equals 2? 1,000 minus 1 is 999. Yeah, when you divide that by 99, it's still going to be greater than 2. What if you take n equals 1? Then you would get 99 over 99, which is 1. So as long as n is greater than or equal to 2, then 10 to the n plus 1 minus 1 over a is going to be greater than 1, thus at least 2. And so this is a great proof strategy. If you know something is an integer, if you can show it's greater than 0, it must be at least 1. If you can show it's greater than 1, it must be at least 2. So we know once n is at least 2, the first factor is going to be at least 2. What about the second factor? Well, the second factor has the plus 1 rather than the minus 1. So in fact, for the second factor, if you take n equals 1, you're okay. Second factor is at least 2 if n is greater than or equal to 1. So only chance for x to be prime is for n in 0 or 1. And then we just check. N equals 0, that gives us 1, which is a unit. N equals 1, that gives us 101, which is prime. And so there's a lot of really nice ideas in this problem. A lot of it comes down to trying to find how can you tell if a number is composite. One way is to give a factorization. And again, I don't have to have a complete factorization. I don't need to know which primes everything is. I just need to know I can write it as a product of two numbers where each number is at least 2. And as long as I can do that, I know it's going to be composite. How many of you have taken abstract algebra? Okay. Okay. I actually have not taken abstract algebra. I've taught it, but I've never taken it. My math background was a little interesting. But there's a beautiful result called Fermat's little theorem, where you can actually prove a number is composite without giving a factorization. So here, we had an explicit formula for x. It's an alternating sums of powers of 10 squared. I made a little bit of an algebra mistake, which I'm actually not upset that I did. I know this is being posted on the web, and people can go, haha, this is your professor. You can't even. It happens. It happens to the best of us. We make mistakes. The question is, what do you do when you make a mistake? How do you correct? And if you notice, there's a couple of things crossed out and whatnot. I'm trying to fix it. Bad idea. Take a new piece of paper, start from scratch. When you have something written in front of you, it's going to keep influencing you, and you're going to try. It's just better put it off to the side, take a new piece of paper. You've got plenty of time, and just work on that. And so after a while, it's like, it's not worth it to keep trying to modify this. Let me just start all over from scratch. We had some factorizations, but unfortunately, we ended up getting into a trivial cycle where the u-1s canceled. And so that told us this was not a good way to represent it. So do we have a better factorization? And the better factorization was, looking at it as 100x minus x, looking at it as 99 times x, and then seeing, okay, now we have two better factorizations. All right, so we've got about 10 minutes left. Any preference? I would say I don't want to do 2004 with just 10 minutes left, because there's some fun stuff in that. All I'll say right now, when you're looking at this, the key things that matter is 80%. When you're reading this problem, you should be thinking about 80%. Why are they choosing 80%? What's special about 80%? When you think of 80%, what do you think of? 4 over 5. So there's really a 4/5 going on. So the question is, which fractions might this be true for? And you should start gathering data. And it turns out it does have to hit 80%. So no matter what you try, you will hit 80%. If I give you 3/5, it's possible to come up with a sequence where she's shooting below 60% and then moves to above 60%. So there's something special about 4/5. And then you ask, in general, which fractions have this property? And we can call these, Chanel-O'Keel numbers, or Chanel-O'Keel probabilities. Which probabilities must you hit? If her shooting percentage was continuous, would she have to go through 80%? If her shooting value is continuous and she starts off shooting below 80% and ends up shooting above 80%, does she have to go through 80%? Yeah, what theorem is this? IVT, intermediate value theorem. This is one of my favorite theorems, right? If you start below 50 and you end up above 50, you must have been 50 at some point. Okay. So that's a fun one to do, and we'll do that one probably next week. Okay. We still got about 8 minutes left. We could do either 23 or 94. 94, okay. So we have a sequence of positive numbers. Do you think it's important that the numbers are positive? If we want to put, yeah. So if they were all 0, then the result would be true and it would not diverge. So whenever you're given assumptions, you always want to ask and see, are these assumptions important? So yes, if they're not positive, it fails. So one thing is to start looking at numbers and just writing them down. So we have A1, A2, A3, A4, A5, A6, A7, A8. And we know A1 is less than equal to A2 plus A3, right? A2 plus A3. Okay. Oh, another way of saying that is A2 plus A3. This sum is greater than or equal to A1. Okay. What about A4, A5, A6, A7, A8? I'm sorry?
A4 and A5, some should be A2.
So this is going to be greater than or equal to A2. And what about A6 plus A7? And what about A2 plus A3? A1. So if I look at A2 plus A3, that sum is at least A1. If I look at A4, A5, A6, A7, that's at least A1. What do you think I should look at next? A8 to where? 16, 15, 17, something like that. It's basically, this is called a dyadic decomposition. We march in powers of 2. So we keep taking blocks that are twice as large as before. And when we do this as we march down, well, the sum is clearly going to diverge. So you might have actually seen this with the harmonic series. So harmonic series. So Hn is 1 plus 1/2 plus 1/3 plus ... plus 1 over n. And the question is, what does this sum to? And if you know calculus, this is the integral test. 1 plus 1/2 plus ... plus 1 over n is approximately the integral of 1 over x dx. X goes from 1 to n, which is the natural log of n. And once we hit college, we don't use log for, I'm sorry, we don't use ln for the natural log. We would normally write this as just log of n. And whenever we write log, it's always the natural log because calculus is good. But I'll write both because I'm not sure who's watching this. And then you can do a little bit better job with upper and lower bounds to actually estimate just how much you're off by. But what's going on here is one of the ways that you can prove that the harmonic sum diverges and get a really good estimate of this with elementary arguments is to look in blocks of increasing size. So we would have 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/16. Okay. In each one of these, 1/3 and 1/4, they're both greater than what? Well, 1/3 and 1/4. What fraction of 1/3 and 1/4 both greater than? They're both greater than 1/5, but there's a better fraction that they're both greater than. They're both greater than 1/4. So this is going to be at least 2 times 1/4. Over here, what are they greater than? Each fraction is greater than 1/8. And so this will be greater than or equal to 4 times 1/8. For the next one, we have 8 terms, and each one is at least 1/16. So this shows you the sum is going to be at least 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And that's going to give you a lower bound that's going to be on the order of the log of the number. So it's what's the highest power of 2 we can get before we cross that 1 over n threshold. And you can see, again, this is just an elementary argument. This, choose k so that 2 to the k less than or equal to n is less than 2 to the k plus 1. So k is the log of n base 2 is going to be less than or equal to the log of n base 2, right? Which is the log of n over the log of 2. So the nth harmonic number, we have at least k groupings. Each of the k groupings gives at least 1/2. It's going to be at least 1/2 times 1 over log 2 times the log of n. And this gives us a lower bound of some constant times log of n. You could similarly get an upper bound, right? With 1/2 plus 1/3 plus 1/2 plus 1/3, each one of them is at most 1/2. 1/4, 1/5, 1/6, 1/7, each one is at most 1/4. You can get upper bounds. And this shows you that the harmonic numbers are on the order of log n. I don't know what the constant is. It turns out the constant is 1, but it's an elementary calculation. I don't need calculus to do this. If you remember the p series from multivariable, the sum of 1 over n to the p, it converges if p is greater than 1, it diverges if p is less than 1. If we had like 3 more minutes, I would show you how you can elementary show that that converges. So I'll try to put that in the bank. All right, have a good rest of the day. Let me stop recording.